Okay, so we're continuing in 8.3. We were just talking about this flow. We in this example we were just kind of picking paths at random and seeing how we would do, and we ended up finding that the max flow was 7. But I didn't want to finish this without some notation, and so this is the way the notation would look, right, for each of the flow values and then the capacities. Right, and I also wanted to mention that we have the value of flow F, and how to find the value of flow F. Well, there's a couple ways you could do it. You could either sum the flows going into the terminal, or you could sum the flows going out of the source. And so I believe we will just go ahead and sum the edges out of S, Fe, and that is the current value of the flow. It says edge out of S, right? Good. And so in this case, we would have 2 plus 6 plus 3, right? Wait a minute. I don't think we got that far. Was that a 6 there? Nope. That was a 2. Okay, did you catch that error? So now that's a 2 plus 2 plus 3. Okay, thought there was an error there. That's 7. Okay, so the value of the flow right now is 7. All right. Now there's a couple of other things we wanted to define about this graph before we go into the formal algorithm, and that is a cut. So given the graph G, let's just go ahead and say given G, cut into two sets A and B is a partitioning of the vertices of G, where at least S, the source, is in A, and the terminal node is in B, and then the other vertices would just be in any set, either set. Okay, so let's just maybe do a quick example of what a cut will be. So, for example, we might say that set A always has to have S. Then how about 1 and 2? Oh, let's say, 1 and 2 is fine. And then set B would be 3 and T. Okay, so that is the cut. This is the cut is the set of edges going out. Let me back up when I said that. The cut is actually the partition, right, into A and B. But then we have what I wanted to define next was the capacity of cut AB. It's abbreviated as cap AB. Okay, and so it is the sum of the capacities, capacity CE, for all E from A to B. Okay, and so in this case, you could see here we have S1, 2, and 3T there. So what are the edges from A to B? S1 is an edge, but that's contained in A. In fact, maybe it would be good to think of this as a physical cut, right? Because then the edges from A to B is edge 1T, edge 2, 3, and then edge S3. Okay, and so then the capacity of the cut would be the sum of the capacities here, 2 plus 2 plus 3. Okay, so in this case, in the example, we have F sub, what were the numbers? 1T, f sub 1t plus f sub 23 plus f sub s3, and that was equal to, I should have just drawn this over there, 2 plus 2 plus 3. Right, and that is the capacity of this example, AB. Very good. Okay, so that is the capacity of the flow. Very good. Now, you might be thinking that, was that a coincidence that the capacity was equal to the maximum flow? And it was in this case. So in general, there is a relationship between them. And so let's just go ahead and write the flow value lemma. So in general, what happens is that the value of the flow is flow F is equal to the sum of the edges out of A, F sub E, minus the sum E into A, F sub E. Okay? And so in this case, did you notice we don't have any edges going backwards, right? There are no edges going from B to A. That's why the value of the flow ended up just being that, because there wasn't any edges back into A. Good. All right. Now, there's a reason that we're looking at these cuts, and that is the cuts give us a way of indicating, or as they give us a way of checking to see if we have a maximum flow or not. Okay, and so what we're going to do next is, let's see, before we actually get into the algorithm, there's one more thing to talk about, and that is everybody's favorite thing to talk about is a residual graph. Residual graph. Okay, and I should say the book does a terrible job talking about a residual graph. Okay, so we're going to be given graph G with a flow. Okay, and what we're going to do is to build the graph, G sub F, that's going to be called the residual graph. We do two things. For each edge E, let's see, maybe I should say E equals UV, so I want a direction there, and FE greater than 0 on G. On G sub F, we create a backwards edge. So G sub F and G are going to have the same vertices, but the edges are going to be different. Backwards edge, and the capacity along that is going to be, oh gosh darn it, I'm running out of time when I'm trying to get this, with capacity F sub E. We'll slow down here and do an example, but okay. So that again is for each forward edge, for each edge UV and a positive FE, right? On the residual graph, we're going to create a backwards edge from V to U with capacity F sub E. Or sorry, that's a residual capacity. This is actually the flow value, right? Better be careful of that. Okay, you'll see how this works. For each edge, E equals UV, and F sub E, right, between 0 and C sub E. Notice that that is not equal to, just less than, on graph G. Create a forward edge. Gosh darn it. My thing's moving around on me. Why is it doing that? Creating, jeez. create a forward edge on G sub F with flow F sub E. Oops, I'm sorry. It's the residual capacity, which is CE minus FE. Okay, I'm going to stop here so that in the next video, we'll review these two rules quickly, and then we'll actually do a couple of examples.